of data science in UIU. And too bad that she wasn't here the second week when we had this interesting evening discussion about how can physics tools help the DL practitioner, because that's what she will, some of the elements of the answer to this question should be in her lecture. Julia.
Thank you very much. Can you hear me? With I had to, the female fashion is not very convenient for giving talks, as you can see. So I hope you can hear me. I'm very pleased to be here. And thank you very much, Lenka and Florent, for letting me come to this absolutely wonderful place. And yes, it's true, I was not here in the first 2 weeks. But I secretly planted, I don't know if he's here, my student Nikos, who reported to me, and oh, there he is, yes. So in general, for any question that you have on my talk, you should go to Nikos first. But that aside, so there were beautiful lectures here with a lot of theory. So I view myself here in this crowd, I think I'm practically, I'm an engineer, like a mechanical engineer. I'm not, when I go out to the world, they think I'm a theorist. But in this crowd, let's say I'm a practitioner or more of an engineering type of person. So I will ask the question. So I will give you some things that I know. So what's my background? I mostly come from computer science. I mean, I have a bit of a math and a bit of a physics background, but the language I grew up with is more the Boas Nati type language. So I'll give you a little bit of that flavor because, as I understand, we have to do some proofs on the board. I can't just talk. And so the ingredients in this lecture, what will I talk about? A little bit of sample complexity, computational complexity. I mean, you can't just, we have to, but I will basically wave my hands and try to give you intuitions. I won't be very much into proofs. I want to speak also, partly in my first lecture and maybe later, let's see how it goes, about symmetries and invariances and methods like this. Of course, I'll speak about the NTK, and I'm very grateful to Yasaman for her beautiful lecture that already set the stage, and I understand Andreas spoke about these things and others too. Physics intuitions, and I do want to speak about some practical problems because one thing is here in this school, we have this thing, we're looking at this deep learning and we're saying, wow, it works, but nobody understands why. Let's understand. And that's great, and we need to understand it. Why does it generalize with all these parameters, all that stuff? But frankly speaking, there are problems out there that people haven't solved. Deep learning, maybe it kind of works. But for instance, adversarial robustness is a big open problem. I mean, that just hasn't been solved, as in hasn't been built. It's not that we need to understand it, we need to solve it. So let's see what we can do with our techniques for this type of problems. Other things I want to mention, for instance, are, if I get to it, pruning. So people are trying to cut neural nets. What can we say? We as, the theorists on that. Architecture, search, physics-inspired neural nets. I will speak about, I will start with examples from data distillation because that's a recent application of NTK that we like and that we build on in our work. So I will try to, speak about these practical problems of which I have some sort of superficial understanding. So probably in each time I will speak, there will be somebody in the audience who knows more than me, and please feel free to chime in. But I'll try to give you a broad kind of spectrum of things that we would like to solve in deep learning practice, perhaps. All right, so my understanding is that you need to start with a triangle. I saw it with Michael Jordan. There was a triangle. And also when I speak, as in my head as a director of Center for Data Science, when people ask me what is data science, I always put a triangle. And I say, this is math, this is statistics, and this is, what was the other thing? Data, or whatever. But here, it's a triangle that I stole from our gracious host, namely Lenka. And that's the triangle as to what makes deep learning work. And this is all Lenka's ideas and Lenka's graph. So there are 3 ingredients, right? One is the data, and that's the one I would like to focus on in these lectures. There's, of course, the model, the architecture, the neural net, and there is also the optimizer. And we have seen, or you have seen mainly, these beautiful lectures of Nati on the interplay between the model and the algorithm, where we get these biases, right? These implicit biases which come from the optimizer and the model, right? So you have seen these things. So that's one thing. I want to focus more on, so what are these things? So model is, what I mean by this is the architecture, the parameters, the depth, convolutional, non-convolutional, all that stuff. The algorithm, SGD and GD, our favorite one, but also others, regularization, and of course the data, which I want to focus on more, because part of the reason why deep learning works is because the data is what it is. Images are not just random Gaussians. They're not just random images. They are something. So there is structure. There is a certain dimensionality. There are invariances in the, translational invariance, for instance. And also, if I hopefully get to it, provenance. I mean, if the data is from physics experiments, maybe we can put in something about physics into that, into the models. So I hope to mention at least something called Hamiltonian neural nets, which I can do relatively fast, where you put some physics into the neural net directly. All right, so as I said, this is what Nati spoke about, among other things. And this is more what I want to speak about. So the interplay perhaps more between data and model, but there will be a bit of the algorithm as well. So let me start with some sample complexity, something more computer sciencey on the inductive bias with the tools of sample and computational complexity. Also want to build on what Boas has told you. So it's very convenient that he gave the lectures just before me last week's. And then in the data theme there is, and with the model, is adversarial robustness and perturbations and pruning, physics-inspired neural nets, all that stuff. And kind of all this is described or relates to invariances, symmetries, but also the NTK and the neural net Gaussian process kernel, which I will speak less about, but maybe Yaseman will mention more, I don't know. But in any case, these are the tools. Let me start with inductive bias. Okay, so just to give you a flavor of the kind of tools and ways people prove these things. So we know everybody is like folk wisdom that we better use a convolutional architecture if we want to get anywhere, especially in vision and other problems, right? So it's known that convolutional architectures perform significantly better for more complex data sets, at least, than their fully connected counterparts, at least given the same amount of data, right? And of course, what people say is, intuitively, that's the inductive bias. So what does it mean? It means that the convolutional net, which is invariance or perhaps equivariance, depending, matches the underlying structure of the data better. That's what people say, right? Maybe also, a convolutional net, very often you have weight sharing, right? I mean, you use the same window, same filter that slides over the data. So maybe there are fewer parameters, and we generalize better because of that. But how do you make this rigorous, right? That's this one question. And there's two works that I just want to present to you. They're not mine, but they're nice nonetheless. And they are, as I said, partly build on what Boas has taught you. So how do you do this as a computer scientist? As a computer scientist, you try to prove separations. So the problem here is, of course, that you can build a big fully connected neural net, and then it's at least as strong as a convolutional one. Because all you have to do is learn the weights so that you zero out the ones that are not supposed to be in the convolution, and you just learn the convolution, and maybe you even learn the weight sharing. So you can, of course, embed a convolutional network into a fully connected network, right? Obviously. So that's not so good for proving, because it doesn't mean that we're not proving anything about the expressivity here. You can't use these proofs, so that's annoying. But you can still try to prove something. And there's a beautiful result I found, which I will not present to you, but I'll give you the intuition from it, by Li Zhang and Aurora last year, where they find a task in d dimensions so that they can show a convolutional net can do it very fast with very few samples. And a fully connected net will need at least, d is the dimension of the data, d squared samples. And they give a beautiful intuition. I'll only give the intuition, and I'll tell you what the task is, but I won't prove it because I don't see what's gained from that proof. And then there is a second result that I like very much by Malach and Shalev-Schwartz, also last year, which relates to Boas, which is why I like to present it, where they show that if you have a hidden pattern, let's say parity, and Boas showed some nice experimental results on that too, but if you have a hidden, think of it as parity or any pattern that only is on a few number of bits, and they're consecutive, okay? Then a convolutional net can do it can solve this, can find this hidden planted structure very fast. and any reasonably sized, fully connected net will not be able to do it efficiently. And if you think again about these, this is a more sample efficiency. It relates to complexity, but in the end it shows that you need many samples or many steps, something like this. And in fact, there was a recent, I was a bit puzzled. So again, I don't know much about transformers, but you must have heard that recently transformers have migrated from there where they belong, like their language thing, to vision, right? You've heard that. And because, I mean, it took a long time for these transformers to make them work on images. And one thing was that this, I think that work was either done at Google or Facebook, I forgot where, because what happened is that in order to train these transformers, it didn't work on ImageNet. They had to use some enormously huge, maybe someone you know this better, I think it was Google, proprietary database that was not available, which was not millions of images, but like billions of images or something, in order to train this transformer. And then it worked on vision tasks. And relatively soon, and I was surprised that it took even some thinking on that, people came up with a convolutional transformer, so where they put that inductive convolutional bias in there, and lo and behold, you could now train it on smaller data sets, if not even ImageNet. So you see there was even a manifestation in recent, I think in the last year or two, of this phenomenon where you need tons and tons of data if you're not smart about your architecture, and then when you become convolutional, it gets faster. All right. Oh no, so so now I want to get the board, if I can, and write something on the board. And you have to bear with me, so I'll try, it's only recently that I got glasses, so I don't know, it's the first time I give talk where I have to look at my notes, and I don't know how that will work, so bear with me if I don't see.
These results allow arbitrary depth for
Sorry.
These results, do they allow arbitrary depth for fully connected and
Yes. So the fully connected can be anything, any fully connected. Yes. The ConvNet, it's a proof for an upper bound. So you just give you the ConvNet, and it's very simple actually. But for the lower bound, you allow any fully connected net. And let me give you the intuition first. So let me start with the intuition from the Aurora paper. It's Li, Zhang, I think, and Aurora. So I'll start with this intuition from Li et al. In this, 21 paper. So how do we show that a fully connected neural net, what's the intuition? Oh God, that's horrible. Okay, so what's the intuition that a fully connected neural net can't do something, right? So what can we use possibly? What is it about the fully connectedness that makes the thing hard? I mean, you would think fully connected is a good thing, but what is it that makes it hard? And so the idea, and I'll just outline this idea, is the equivariance of gradient descent of GD. Okay, so what do I mean by this? And what do they mean by this? It basically means that it forces the algorithm not only to learn there's a task it needs to learn, it forces the algorithm to learn all the orthogonal transformations of that task too. Because gradient descent is kind of blind to orthogonal transformations. So let me make this precise mathematically. And let me just start with something simple, namely linear regression. So as I think, like everybody, my data lives in RD. I think there was a bit of a discussion with D for me, always data dimension. I think, Yasaman, we had the same notation. At least for today, we're being consistent. Eric, you better, where is he? You better call it D. All right, and YI, let's do linear regression. So R, right? And so our data vector, our data matrix, right, lives in basically, so the number of data points is n, okay, n cross d, and so the big label vector lives in Rn, okay, right? So that's our data, and our loss function. Let us assume even, but that will generalize. I'm just giving you ideas here. Our loss function will be, for linear regression, let's say it's L2 loss, which just means we have X transpose W minus Y as a vector, and that's what we minimize, right? Linear regression, very simple. All right, so what does gradient descent do? Gradient descent iterates, right? So gradient descent, what does it do? It iterates, so it makes steps on the weights, on the weight vector, on the parameters, which also live in right? The weights also live in, they also live in RD, right? So it's linear regression here. All right, so what does the weight do? They go with the learning rate, right? And we take these gradient steps on the loss function. So what that means here is, I'm sorry, I'm just going to be deliberately slow in my computations in the beginning, and then we'll speed up. So here, if we take that gradient, what do we get? Here's the learning rate. Here's our data. I'm plugging all this in, and I get X transpose W, right, minus Y. And let's call this the update function. So this is the function that I use to update the weights with the data and the labels, right? So every gradient step, I apply this function with the same data and the same labels, but the weights, get updated with that function.
So can I just ask about the notation? I'm like confused about the dimension of X. You mean for it to be D by N?
What did I write? N by D, you wanted D by N?
Well, I think you're taking X transpose W, right?
Right, so I'm thinking of it as data being chuck, right? Every column is a data point.
Yeah.
Oh, you don't want me to transpose it?
If every column is a data point, then it's probably...
You want it the other way around. D by N. Okay, so you want me to do it this way? All right. Yes. Okay, let's do it this way. All right. Anyway, so coming to this, once we're done, right? Let's look at this now. And this is our gradient descent, and eventually we converge. We know that linear regression with gradient descent works out just fine. But let's observe this now different basis, change basis. And what I mean by this is that we change basis for the data. So in other words, we take a vector and we apply it to our data. So this is a rotation now in data space, D by D, okay? And we get our data in a different basis. That's fine, right? I mean, I can rotate my data, that's okay. And what happens now? What I want to show is, if this is then the ultimate solution, so if W star is where this thing converges to, so it would be, I guess, F infinitely many times applied to, right, X, Y. So once we converge, let's say, so what I claim is when we change basis, then what happens is that the final solution, we get the same solution. So in other words, our final solution, when we do it with this data, will simply also be a rotation of the final solution had we not rotated our data. Okay? So I think it's nearly trivial. What I want to show is, I basically want to show in some sense that the L2 loss is invariant under rotation, and hence this function here is equivariant under rotations. I'll do it in a second. And hence, when I rotate my data and I rotate my weights, I get the same solution. That's all I'm saying. For a fully connected linear regressor, so a fully connected layer with just linear activations. Okay, so let's just do it once so that I have a feeling that I do some proof, right? So we can do it by induction. So the induction is that, of course, usually we initialize our weights with a Gaussian. And what's the beauty about a Gaussian? It's like when you rotate the Gaussian vector in a different basis with the orthogonal rotation, it remains a Gaussian. Right? That's the beauty of it. So it's invariant under rotations. So in other words, if we initialize anywhere, then and the initialization is, sorry, let's do this, is invariant under rotations because it's usually a normal 0 sigma squared 1, right? That's our weights, as you've seen with Yasaman also. So, but that aside, now if we compute our recursion here, then what we get is that in that basis prime, if we make one gradient step, which is f of the previous weights, t, of the rotated weight, and y, right? If we write it out, let me do one step here, then we get w prime t minus the learning rate, ux, this is our data, right? X transpose u, right? So when you transpose it, u transpose, right? W prime t minus y. Okay? So that's just applying everything here. And then we can pull out the u. We're pulling out the u, and we're canceling some things, because here we apply the previous induction. So, right? So now I apply, I wanted to say I'll do it by induction, and I forgot the inductive step. So let's assume already that the weights at time t relate to the weights at time t for the other one, the unrotated one, like this. So now I apply the induction hypotheses, and I immediately pull out the u. Okay, so that's then, when I do this, what do I get? Wt minus eta, the learning rate x, xt, wt minus y. Okay? So in other words, what I get is u of f of wt x y. Okay? Which is u of wt plus 1. So what have I shown? I've basically shown that the function f, the gradient update, is equivariant, just so to get the terminology here in. So what that means is, if I rotate the data, I can pull out the u and instead rotate the weights, the output. Okay? That's what it means to be equivariant under orthogonal transformations. Okay? So that's all the observation we need for a fully connected net. And what that means is, because the initial transformation at 0, we're actually rotationally invariant when we initialize, okay? Because it's, that's how we initialize. That means that at the final step, we are also basically getting the same solution in different bases. The algorithm solves the same problem, whether I rotate or not, okay? So it needs to be able to solve all the rotations. It doesn't depend, whether you rotate it or not, it will give the same answer, okay? So that's all the intuition we need here. Because, and so I'm not going to give the proof, but for general fully connected networks, what you can do is you can now have several layers, and you do this type of analysis neuron per neuron for the first layer, and it will still hold. And so you'll see that the whole thing keeps being invariant under rotations. Okay? So I'm not going to do this, but it's kind of clear that once you have this invariance property, it keeps on fully connected. You can propagate it through. Okay? You rotate the data, and then in each layer, let's see how that works. No, I think you just need to apply it to the bottom layer. Let me think about it. If you apply it to the bottom layer and you're rotationally invariant, then also the outcome, the algorithm will see the same thing at the end. We'll solve the same problem.
This depends on the scalar products, right? So it's because the activation depends on scalar products, so they actually need the
Yeah. So the activation, of course, also only depends on these inner products of the various layers, and so it doesn't matter. For the activation, doesn't see this, basically, and then you go. Ugh. Sorry, you see that's the beauty of using glasses for the first time. All right. So having said that, now just for the intuition, let's assume you want to. I'm just only building intuition and nothing more. But let's assume you would have an algorithm, for instance. A task. It's not the task that Lee et al. Gave, but just a kind of warm-up. If your task was on a hypercube, for instance, so if your task was, for instance, if your data was either, so the basis vectors, let's see, if your data was ei times y, comma y, where y is in 0 plus minus 1, and ei is a basis vector in Rd, 0, 0, 1 in the ith position, right, here in Rd, right? So let's assume your task is you have these vertices along axis parallel, you have these vectors that are parallel to all your many axes in d dimensions, and you're either having a vector pointing in the one direction, and then the label is 1, or you have a vector pointing in the minus 1 direction, and your label is minus 1. I'm just giving you an intuition why this is hard for a convolutional network to do, okay? So if you had such a problem, what would the convolutional network do? The convolutional network would apply some algorithm which we know is equivariant. So in other words, any rotation of this, excuse me, fully connected, sorry, fully connected. So intuition, what I want to say is this is hard for fully connected. And what I mean by this is that you need many more samples than you would think you need, right? So to learn this. And so what the fully connected neural net, if it sees this type of data here, what does it do? I mean, it sees the data, but we know it's invariant under rotations, right? So all the convolutional neural, I'm being intuitive here, but all the fully connected neural net gets, basically, all it can infer, because it has to be equivariant under rotations, it can only argue about the inner products of these vectors, okay? So any algorithm, any FC algorithm that needs to be equivariant, that sees this data here, right? Let's see, it sees data points x1. These are data points here, x. These are the x's, right? So x1 up to xn, it sees some data points. With all this argument, intuitively, all it can do is argue about the inner products of the vectors it sees. Never about the absolute position, because it needs to be equivariant, right? So it doesn't know whether this thing is axis aligned or not, because it has this property that are kind of derived here, okay? So what that means is that de facto, I'm being a bit flu here, it can only implement some sort of function that depends on the inner products. So let's assume this is the data it gets, okay? And now it needs to make inference on some point, okay? Here, so it's supposed to output whether the point is a plus or a minus, let's say, okay? But this can only basically base itself on the inner products with the data it has already seen itself. I'm being very vague here, okay? Xn. Because the algorithm can't distinguish anything rotationally, it must be rotationally equivariant, all it can argue about is inner products, right? Because it has this rotational symmetry. And now you can see why there are lower bounds on the sample complexity. Why? Because let's assume n is smaller than d over 2. Right? So remember, the Aurora, the sample complexity bounds are always as a function of d. In Aurora's case, it's d squared, but let me give you a bound that's at least d over 2 here. So what can the fully connected network do? When it only saw less than d over 2 of these vectors, it can only argue about the inner products, and if it gets a new data point, with probability 1/2, it hasn't seen that space before. If you have n over 2 vectors that are orthogonal in a space of dimension more than twice that, then with probability 1/2, you're lying outside that space. Okay, so let me write this down. With probability bigger than 1/2, the inner product of x and all the ones that you have seen here before, j, whatever, is 0. Right? Because you haven't, probability 1/2, your vector allows outside the ones you have seen, the span of the ones you have seen before. Then what can you do? You can only guess, right? You have 0 information. So the best you can do is guess, obviously, right? Because the label here that you get from this data point is, of course, either plus minus 1, but you don't know. There's no indication to see because we're orthogonal. So the best you can do is guess, right? So that means that the algorithm is wrong with probability at least, right? At least 1/4. So with probability 1/2, it gets a point outside its span, and then with probability 1/2, it gets the wrong answer at best, right? So that means in order to get some low error probability, you need to see at least half the data. Excuse me, d over 2, you need to see at least d over 2 of the data, just from this property of being equivariant. Okay, so this is just for intuitions. Okay, and then what this paper does is, after building this intuition, they actually prove a separation of d squared, which I'm not going to show, but it's basically based on all these ideas. And their function, just for those who care what their function actually is, the separating function that a convolutional one can do and a fully connected cannot do, what they do is they have a function that is basically h of this x's in Rd, right? Let's say in R2D is the sign of the first d bits, right, squared, minus the sign of the second That's what they do. Yes, I want to square it because I want this rotational kind of, there's a bit of a rotational idea. Let me just write it here. And
the x's are not plus minus
G.
1, I guess, but still, like, I mean,
2D.
here the sign,
it's the x's are, they're on the Boolean, yeah, it's a Boolean cube thing.
so you cannot square it here because then the sign is, like, you cannot square them inside the sign. Maybe
Because it's positive, yes, because it's, you are absolutely right. It's this. Sorry. Yes, so you square the first half and you square the second half and you look at the sign of the difference. Is this good?
you square outside the parentheses. You look at maybe the bias from 0 in the first half minus whether it's bigger or smaller.
The first half, yes, and then, yes,
from the
exactly.
second
Yes,
half.
yes,
So
yes.
it's like squaring
Yes,
outside the parentheses.
yes, sorry, yes.
Outside, right?
Squaring, no, you square, sorry.
I mean, the sum of xi is
The sum of the first squares minus the sum of the second half squares.
Just whether the sum of the first square is bigger or smaller.
Yes,
So, if it's Boolean cube, that will also will always be 0. But
yes.
maybe what they meant is like the sum of the xi's, all that squared,
yes.
minus the sum of the second.
That's what it is.
xi's,
Yes.
all
Okay,
that
sorry.
squared, and then-
Yes. Okay, I'm sorry. I apologize.
One-
We want this.
Yes.
I apologize. And now, I'm sorry, and just because to prove you right, the convolution architecture they use is a very cheaty one, but nonetheless, it's simply, you have here your bits of x and the other half, right? And then you do here one convolution and some other convolution. Is that what they do? And then they have a nonlinearity, which is just squaring the thing. Something like this. Yes, it's cheating, but nonetheless, this solves the problem easily, and you can see, and then you have these two, right, the pooling. You can easily see that this basically you just need to, I think they even have, excuse me, what they do is they one convolutions. So they do weight sharing here, okay, so they have convolutions with just one, window of size 1, and they do weight sharing, W, 1, and then they just have to learn basically that these have to be opposite signs, something like this. And similar rotational arguments show that a fully connected, I don't want to go into this, but it's not an easy proof, but similar arguments show that a fully connected network can't do this at all. Okay, but I want to focus on, this is a sample complexity proof, so this is just, you need these many samples. I want to focus, I want to give you more intuition on the second result by Malach and Shalev-Schwarz, where they actually show maybe slightly more interesting problem, I find, that relates to what Boaz taught you, to prove another separation between convolutional and fully connected. So if I may...
I'm a little confused about this conv architecture here. Is sigma ReLU here? Or sorry, d squared. And then is there any sort of pooling before the nonlinearity is applied? Or is it applied?
No, so this is just, think of it as a convolutional window that goes across here, and then so all these weights have the same sign, and then you just square them, square the sum of these things. So think of it as pooled here, and then pooled here, and then sum together.
So the weights, the parameters are just like a single number. Like
It's just a single number. It's just literally a single number.
Like this network has like, I don't know, 5 parameters.
It has 5 parameters. I mean, it has 2 parameters, I think, or 3 or something. Yeah. It's cheating, but it still gives you beautiful complexity separation.
Is there something about the structure of the task which we should expect to be pulled and more realistic?
That's a good question. So I feel I would like to answer this question more for the second separation I give now, which is a little more intuitive, if I may. Honestly, I don't get much intuition out of this, except this looks kind of right with rotational invariance. It's kind of hard. But allow me to answer this for the next one, if I may. So let me give you the other separation. Again, mainly intuitions for it. And it's in part also to teach you to not be afraid of proofs in theoretical computer science, which I spoke to Boris the other day, and he told me, oh, this paper has beautiful results, but it's horrible to read, has all this computer science language. So, because I don't think it's, you just need to read it. You just need to know, when I see a Gaussian process, I cringe, right? I don't, but this I don't cringe because, I'm used to. So let me just give you basically a little bit of less fear when you see these things. Because in computer science, there's basically only, I don't know, Boas, I don't want to insult you, but there are maybe like 10 things you need to know, and when you see them, then you kind of know what they mean. Okay, let me say what I mean with this. Okay.
You're generous.
10, okay, yes, sorry. For Boas, 10 for me too, I'll show you the 2 that I know. Yes, sorry. Oh my, yeah, so yeah, okay.
It corresponds, so I have D inputs, and then in the first hidden layer, I have already only 2 neurons?
Yes.
So even if this was fully connected, I would actually have only twice D plus 2 parameters or something like that.
Yes, but for the fully connected, we kind of show any fully connected can't do this. And here you have this weight sharing, that cheating kind of fully connected architecture.
I understand, but even if I took the same architecture and made it fully connected, if I only have 2D parameters, I should only need something like 2D samples and not D squared.
I see. Can we? Okay. Let me do it right next time. I'll come back to it and I'll answer this precisely. I don't. I can think about it. We'll take time. If you allow me, let me do it properly. Okay. Next time. Let me just go on with the other results now. So this is Malach and Shalev-Schwarz, as I said, 21, and let me just write down. What the problem is, because you'll recognize Boas's hand in that. Namely, the function goes from the Boolean cube, so there's nothing I can do about this. So plus minus 1 to the n goes to plus minus 1, right? So that's what it is, computer science. But it's a task where there is a hidden index, there is a j star, such that, and a function g, which is defined on k indices, 2, 0, 1, 2 minus 1, 1, I should say. Okay? So there's a big function on a bit string, and there's a small function on a bit string, such that f of x1, these are the xd, sorry. These are the input is equal to g of x j star x j star plus k minus 1. Okay, so what we have here is we have this big bit string, and inside that big bit string, we've hidden a consecutive pattern. Okay, and Boas spoke, so think of Boas's lecture, where G was simply the K parity. Okay? Okay, so that's what we need to do. All right. So I'm actually for the lower bound. Why can a convolutional net not find this? So I'm not going to prove this much. I keep saying this wrong. Okay, so statement 1, and I'll only wave my hands, but I'll refer to Boas mainly. Hard for the fully connected. Okay, so we have seen with gradient descent. Okay, so we have seen that the fully connected network is invariant under rotations. Now here rotations we don't even need. In particular, a special class of rotations are the permutations, as you know, right? I mean, just permuting bits is a part of the family of rotations. And so in particular, let me just say, because fully connected networks, they are also equivariant under permutations, obviously. Because the fully connected layer cannot see whether it's consecutive or not. All the weights are symmetric, so you can permute, it's the same thing. So why does it relate to Boas? I mean, probably the audience can already tell me why it relates to Boas, or at least Boas can tell me why it relates to Boas, I hope. So what we see here is that for the fully connected net, it needs to resolve a harder problem. The fully connected net needs to basically solve, so that means FC, right, needs to solve planted. Did you call it planted? Did you call it planted parity? I don't know what you called it.
Random sparse parity.
Random sparse parity. Can I call it planted parity? Yeah, sure. Yes, okay. Planted parity, planted pattern, I should say. Not even parity, but in particular pattern, K pattern, right? So what that means is, because the thing is fully connected and hence invariant under permutations, it needs to solve the K pattern problem for any pattern for any indices, right? And now this is, I mean, computer science, they thrive on these problems. This problem is called actually, it's often called the Keyhunter problem. So, Keyhunter, which has a long, long history of which Boas knows much more than I do. But the point is, it's hard. It's one of these things that computer scientists love because it's hard. It's hard to solve. There is no known algorithm. And what Boas showed you is that the parity, so one special instance is when G is the parity. And what Boas showed you that in the SQ model, remember the SQ model? So the statistical query model basically doesn't give you exactly the outcome of a query. It gives you a sample average of a query, right? So what the SQ model does is when you have a function, you can ask any function about the data, anything, in particular gradients, okay? And then what the statistical query model does, it gives you the expectation. So this is a function on the inputs. It gives you the expectation over the inputs. Let me write it down like this. Maybe I should actually copy from my notes, right? So it gives you the expectation on the inputs with some error, the oracle. For all such functions, it gives you the expectation according to the distribution of the data of this function, plus some noise. And usually the noise is bounded by something like tau, which is the precision of this SQ oracle. And you can think of it differently. You can think of it as having samples of size roughly 1 over tau squared. It's the same thing. Whether you get within error tau or whether you get samples of size 1 over tau squared, tau is a small number, it's kind of the same thing. And what Boas argued is, or maybe Boas didn't argue, but intuitively, gradient descent works on these batches, right? And what gradient descent does is it gets some sort of averages of something, the gradient, but doesn't matter, but some average function. So this is think of it as the gradient, right? In gradient descent. Gradient in SD and GD, right? So what gradient descent does in the fully connected net, it gives you slightly noisy samples, which correspond to this in the statistical query model to these queries. And Boas showed you that parity, in particular, is hard, needs a lot of samples, right? So I'm waving my hands here, obviously, and this is me waving the hands, not them. So they actually prove something here. They use similar tricks that are used for all these proofs. Namely, they do something what's like the Fourier. They look at the Fourier coefficients, discretes of these functions, but they show that in reality, any gradient is very, very small, unless the neural net is large. Basically, that's what they show. But I don't want to give this proof. It's a very, it uses the invariance on the permutation and all that stuff. I don't want to give it. But intuitively, if you believe Boas's results, and if you believe that gradient descent is like querying a statistical query model because you get averages over data, if you believe this, then you kind of see why it's hard for a fully connected net. Is that okay?
Just say how specifically from the result I showed would be that the product of the number of samples and the number of steps would have to be at least something like d to the k.
Yes, right. And by the way, when I say k, so I'm sorry I forgot to say this, but you should think of k as log n. N, remember, log d. D is the dimension of the data, right? So think of k as log d. So not constant, but just slightly non-constant. And then already any good algorithm needs size at least d to the log d. Okay, so it's hard, yes.
So here the function is in the very beginning -1 to the power of d, right? Not n. Yes.
Which function? Sorry.
In the very beginning. I mean, that's not d.
The task here? Oh, d, yes, sorry. Yes.
It means that if f is represented as g of something and k is very small compared to d, it means that essentially the value of the function f does not depend on most of the...
Yes, it's hidden. It's a plant. What did you call this? Random sparse. That's a better. So planted doesn't give the intuition. Yes.
Okay.
Right. Okay. So if we believe complexity theory, and if we believe Boas, and if we make a slight leap of faith and believe that gradient descent is a little bit like the statistical query model, then we can believe that fully connected nets have a hard time with this, okay? But you don't have to believe it. If you go to that paper, there is actually a real proof that shows that gradients are tiny. And they are tiny as a function of the width of this network. And so you need a very wide network, super polynomially wide. The network has to be non-efficient in order to solve this problem. Okay, so that's the actual proof, yes?
And the argument that for convolutional network it will be easy.
No, let me do that. I'll do this now. No, I wanted to take the, yes, sorry. I'll do it. Give me a chance, yes. Yes.
A bit more on this K log D. Will it be easier or more difficult if you decrease K with respect
No, if K is 3, what do you do? I mean, you just as an algorithm, not a neural net, but if K is 3, you just check all the possible triples, right? So there are D choose 3 triples, you just check them all and you'll see who it is. It has to be at least log D in order to get a, D to the log D hardness. And then it gets harder and harder. Yes, so now you're asking me, Boas, you can answer me. If D is equal to K, I presume it's still hard. It's
harder, like the lower bound is like something like D to the K and D choose K.
Yeah, so it's D, right? I mean, we're talking about D log D.
Something like D choose K. I guess you just don't want it to get too big because you also need it to be easy.
Right. Yes. Okay, so now why is it easy for the convolutional? So if I can get the screen for a second, if that's okay, I will show you. So if you look at the paper and you are not used to that language, you'll be deterred. Is it showing? Or, It takes a minute. Okay. So in the meantime, I can erase the board. Is it warming up? Okay. So in the meantime, let's see why it's easy for a convolutional while the computer wakes up. Easy, and easy means there is a gradient-based algorithm for a conv net, and it's in fact a 2-layer convolutional net. So let's write it as H with parameters U, W, and the bias, okay? It's a 2-layer net with a I'm going to already cheat because, not cheat, but I'm going to put my filters, the windows of size K, because I want to find the K, right? I want to find these K consecutive. I better use a window of size K. So let's use it. So then here, J equal 1 to n minus K. So these are the windows, right? And there's Q channels. So, Yasaman just gave the whole description, but let me write it. Uj, these are the weights in the outer layer. And then here is the nonlinearity, and then here are the weights W that multiply xj, these bits xj plus k minus 1, okay, plus, and some bias, b. Okay, let's just say there's one bias. All right. Yeah, I'm going to cheat. Of course, I'm going to give you a convolutional architecture that solves the problem. And so I want the K, the size of this window, right, the convolutional window to be equal to K.
Then similarly, we could construct tasks which are easy for fully connected but hard for convolutional, or not?
Oh, easy for fully connected and hard for convolutional. I have to think about this.
For this argument, it should be like for an average or whatever. For a difficult task, it is easy for convolutional. Then I think it really answers.
It will depend on the data. It will depend on, I presume there is a separation the other way. Yes?
I might be missing something, but if the indices that are relevant have to be consecutive, then why is it hard for a fully connected?
Because the fully connected doesn't see that it's connected. The fully connected automatically has a permutation symmetry, and so it doesn't help it that they are consecutive. And the convolutional will use the fact that, just like in images, remember the translational invariance of it, or something about the convolutional structure makes it, helps it to find the. All right, so what I meant by this is the following. So here's the proof of the upper bound from the paper, lower bounds. From the how upper bound global, whatever. I mean, the convolutional easy one. And if you look at it, it's ugly, right? I mean, this looks ugly. I mean, I presume, except for Boas, everybody will find it ugly, including myself. And so what do you need to pay attention to in such a thing, right? If you see, actually, I never read the proof, I have to say. I looked at this statement and then I said, oh, it's so ugly, I'm gonna look where are my clues, right? And so where are the clues in this proof? So the clues are here, namely the weights, right, in this layer here. There's only one layer. This is a convolutional net, right? I mean, just so that you see how it looks like, right? It's basically this convolutional window here. These are the weights, and we're sliding it up and down this input, right? And then we're connecting them with the other instantiations of this weight as it's sliding, and then there are Q channels also, right, of this. Have I written the channels? Actually, where are my channels in this? I also need channels. So let me, what did I do wrong? Did I do anything wrong? Okay, so let me write down what the solution is. So we have a two-layer convolutional net, two-layer conv, and we have a kernel of size k, as you see. But I'm lost where are my, but we also have Q channels. So I view it as a kind of a two-dimensional thing where we have several of these stacked on top of each other. Each of them has a different instantiation of the weights, right? Of the weight window. They all slide like this, but there are Q of them in that dimension, right? Just like Yasserman had, and then we're summing them. So I think here I'm missing a sum over Q somewhere. Probably. Let me see.
I think it's you didn't tell us the dimensions of W.
Yeah, maybe if I write it like this, then you'll get it. So let me write the dimension of W, and that should actually solve my problem. So W is in RQ times K. Now it helps, right? And U, oh yeah, so that's what it is. And UJ is in RQ. Okay, that's what it is. Right, so these are vectors. So these are vectors, and these are matrices, and now it works. And this is a vector. B is in RQ. And Q is the number of channels. Q is it? No, now it works, sorry. Okay, so you're with me? So think of the W like a matrix. I view them as stacked on top of each other, and there are Q of them, and each of them has size K, and they're sliding along this thing. Good? Okay. All right, so now when we look at this proof, what do we see? First of all, we see that the weights, so they're cheating here, but then everything in computer science, first you cheat, and then you make it smooth, and it still kind of works. So cheating here is the weights are not fully Gaussian. They're actually plus minus 1 over K. Okay? So that's one hint. So what does it mean? When you see weights like this, what should you think? You should think truth table of the function G. Okay, that's one thing. Let me see. And then you see the Q, the number of channels there. And what do you see? So numbers we don't see in computer science, 1, 2, 3, forget them. So what do you see? You see 2 to the K log 2 to the K. Okay, so what is, so let's just say K log K or N log N. What do you think when you see K log K? Okay, so what does a computer, so what should Boas be thinking? So for the first thing, you think it's a truth table. And for the second thing, this K log K is the coupon collector. Who has heard of the coupon collector? Everybody has heard of coupon collector, but I say it anyway. So if you have N coupons, can I use N or is it too overloaded? Let's M. You have M coupons, or M cards, let's say, right? You're collecting cards, and each time you buy a candy, you get one of these cards. I mean, as a children, you probably had this, right? You in the Kellogg's, in the cornflakes, there's always a card, and you want to collect all M of them, right? But they're random. They're coming randomly. Each time you get one card, and you want to get all different M ones. How many cards do you need to get in order to be very good? I mean, with constant probability that you got all cards. That's the coupon collector. They're coupons. Okay. So you have M coupons. But you always get them with repetition again and again and again. How many do you need to get in order to have a good 99% probability that you got all of them, at least once, right? So the answer is M log M. Sorry, what?
Is it uniform?
Yes, each time you get a random coupon out of these M with repetition. You sample with repetition. How much do you need to sample in order to be sure, 99% sure, to have all of them? coupon collector, and the answer is, right, sampled with repetition, and then you need, you need m log m such that, with probability 99%, and there's a constant here which I'm not writing, you collected all. You got all m different ones, right? So, okay, so we see these two things, and then I think the proof is now clear. Yes, go ahead. Yeah, I will, sorry. I will go into it, yes, sorry. So, but now, hopefully, I mean, at least for people, now it's more clear what has to happen, right? So, let's assume, so we know our window is sliding here, right? And first of all, it wants to learn this function g. Okay, so we have the sliding window, and it wants to learn this function g. And this function g is basically a function, as I told you, from 0, 1, from minus 1, 1 to the k to minus 1, 1, right? So first we want to learn this function. And this means we want to, let's assume k is 2. You want to learn XOR, okay? Let's say XOR of 2 bits. So x1 and x2. We want to learn the XOR. How can we do this? We can write down all possible ways. Oh, let me write minus 1, 1, otherwise you'll get confused and I'll get confused. Minus 1, 1, 1, minus 1, and 1, 1, right? And then we can write down what the XOR does. So let's assume it's minus 1, 1, 1, minus 1, okay? So this is one of these, it's one of these functions. One of these functions we want to learn, and we can write it as a truth table, okay? And now assume that each of your weights, each of these combinations of weights there is picks one of these. Why? Because the other thing you should look at is the bias. The bias is 1 over k minus 1. So let's just write it down exactly. Let's just write it down with the truth table in this example, and you'll see how it generalizes. For this example, so for instance, let's assume here is our x1 and x2, right? x1 and x2. And they're possible, so now we write 4 filters. Let me write 4 filters. So one filter is like this, one filter is like this, right? I mean, I can't draw in three dimensions. So think of these 4 filters here. And each filter now has either a plus or a minus weight. Plus, minus, minus, plus, and minus, minus, okay? So these are the 4 possible ways these weights can come out, okay? If I just set them. And then the coupon collectors, I add a few more of these channels to make sure that all combinations appear at least once by coupon collector, okay? If I randomly initialize the weights. But let's assume I only use 4 and I have initialized them in a way that I get all possible combinations. Then each of them, right, will pick these values. So if I have a linear combination of these, what I get for these weights is basically w times x, so to speak, will be, right, either minus 1. So the weights are plus minus 1/2, right, 1 over k. The plus minus 1/2 and the x is 1 or minus 1. So if I have plus plus and it hits minus minus, then I get minus 1, right, as a value. So I can get minus 1, I can get 0, and I can get 1 for the outcome of this linear layer with the first filter, right? And in general, you get the values that are basically, in general, you get minus 1, plus 2 over k, and so on, up to 1 minus 2 over k, and 1 if you hit all the weights correctly, right? So each of these combinations of weights multiplied by each of these x's gives one of these values here, okay? You following? Right? Okay, and now I have this bias. So the bias is also cheating. The bias is 1 minus 1 over k. And when I add this bias, then these values get transformed. So in here, then I'll have minus 2. If I add sorry, it's k, excuse me. It's 1 over k minus 1, the bias. So when I add the bias to these possible values, here I get minus 2 plus 1 over k, and so on. This here becomes minus 1 over k, and only this one is positive. Okay? So if I use any function that distinguishes like a ReLU, I mean, ReLU is not exactly bounded, but any function that gives a negative value to negative numbers as a nonlinearity and a positive to positive, let's say I use a ReLU, I use a ReLU, then these all will be mapped to 0, right? All the negative ones, and only this one will be mapped to 1, right? Okay, so what have I shown you now? With my hand waving, I have shown that each of these filters, right, is exactly an indicator function for one exact value of x, right? That's what I've shown you, correct? Okay, and now any pattern, any function can be written as the sum of the indicator functions. So for instance, XOR is -1 times the indicator of -1, -1, plus 1 times the indicator of -1, 1, plus 1 times this indicator times -1 this, right? So it's a linear combination of indicator functions. You with me? Okay. So now you see that with this bias and this slight, with the ReLU and this little bit of cheating, if I have enough of these channels, I get each indicator function, and all I have to learn is these values, right? But there are only 2 to the k of them, which is k is log n, so there are only n of them. D, sorry. There are only d of them, basically, right? So I basically now need to, if I have initialized my weights randomly, I only need to do linear interpolation on the next layer, right? To learn the function. You with me?
So this is like random feature, right?
It's like random features, and then the proof is a bit more complicated than this because they actually show that you can do it with the gradient descent. What they show is because there's so many of these weights and so few of these linear ones that when you do gradient descent, the weights don't change very much. A little bit like NTK. They don't change very much, so you can assume they're frozen in the beginning. Okay? So what's the trick here? Let me just summarize it because I've waved my hands a lot. First, you put enough filters, but you only need to put coupon collector many filters. So that's 2 to the k log 2 to the k, but k is log d, so it's d log d. That's fine. I mean, d is okay, right? So you put d log d filters. That's okay. And then basically you show they don't change very much when you do gradient descent, and all you have to do is learn, as if they were frozen, do linear regression, where we know gradient descent works. And you have to learn all these combinations here. And you also have to learn which of these, right? So you first have to learn in this dimension across all the filters, right? To get the truth table, the value of the pattern. And then you have to learn one of these n, this dimension. You have linear connections both in this dimension and in this one, for the filters and for the layers, right? And then you can learn the function just by learning the last linear layer. Okay? Yes?
So basically you have, geometrically, we have Q neural networks stacked on each other, which are trained separately.
Yeah, you have, I mean, think of this here as I'm terrible, but think of this as a two-dimensional, how do you do this? It's a square here. The last layer is a square, right? One dimension is the filters. I mean, that's what the convolution looks like. The filters are one dimension. This is what Yasaman this morning vectorized, right? She just decided to stack them all together. And then we have to just learn this Q by N or Q by N minus K connections, basically. Okay, so there's more to the proof, but I'm just saying when you see plus minus ones in the weights and you see 2 to the k times log 2 to the k, you can kind of think how the proofs look like. All right. So this is what I wanted to say about sample complexity. And I do want to now come back to, yes?
It's kind of hard for me to get this. It looks like for the convolutional case, it's hard to the network that in some sense already knows the answer.
Because of the k, you're saying?
Yeah, you could do the same thing with a fully connected network.
No, but here it's a question of how many filters do I need. So by the way, you don't exactly need to know the k, right? You just need an upper bound on the k. I mean, let's assume k is 5. If you put windows of size 6, it doesn't matter. They, in particular, will learn a function that only depends on 5 of the 6 bits, right? I mean, so you don't exactly need to know it to begin with. But yes, I mean, of course, that's what that's what inductive bias is about. You do put information about your problem into the architecture. Yes?
So I think the first result you showed was a statistical separation. The second
Yes,
one was a
very good.
separation.
Yes.
I don't know, I feel like my gut reaction is that the statistical separation is more interesting, but can you comment on that?
depends on, I find them both interesting, right? One of them shows you need many, many samples, and the other one shows you need many steps. I think they're both interesting, right? I mean, we want our neural nets to both not use too many samples and not use too many steps. But yes, they're of different flavor, I agree. And that's basically many, this is only two, I selected 2 separation results. There are many more. I want to show one more, I'll be fast on it, for adversarial robustness. There are also several, and there are particular recent ones that are very nice, which are of both flavors, again. Right, because you want to talk about the learner and you want to talk about the sample efficiency. Right.
So, convolutional networks target both locality and invariance. It feels like in the second one, we're really targeting the locality.
Very good. I wanted to make that remark. Thank you. So if you pay attention to this, you will see that, in fact, we didn't really need weight sharing in this thing so much, right? We didn't. So it was more about having this local window. And in fact, it's an open question. I mean, for those, I don't know if that's your flavor of thing, but I think there isn't yet a good separation between weight sharing and not weight sharing. At least I don't know of any. And in fact, I read that paper and it says there isn't one. So as of 2021, modulo their knowledge, there wasn't a separation that said, because here in this proof, we didn't use weight sharing.
Here the weight sharing will kill the architecture. I won't be able to find something which is depends on a specific set of k elements of the input if I have weight sharing. Because if I have weight sharing, any k set will be the same.
No, you could share. No, sorry, you could share the weights here. I think it wouldn't be a problem because it would be then the next layer that would learn which of these have the k consecutive bits. Yeah, so because you have the next layer. So here the proof works without weight sharing. In short, the constructive proof doesn't need weight sharing, and there is no known separation that I know of, or that I think maybe in the last year somebody found it, between convolutional with and without weight sharing. So there are 2 questions about convolutional: is it the weight sharing, or is it the locality of the window? That is true. Okay, let me speed on because otherwise I'll never get to my NTKs. Right. For the rest of these lectures, I will give you, as I said, one more sample complexity lower bound for adversarial robustness, which is just, again, to build intuitions. But mostly I will talk about what can we do with the tools that you like and cherish, like the NTK. And what would you like to understand better? And of course, the questions that you have studied, of course, generalization with overparameterization, double descent, implicit bias, role of depth, role of width, and Yasaman has spoken about this already and will probably more. So these are interesting questions. But for the practitioner, it's more like, and that's happening a lot now, and this is actually where I would like to solicit these communities. What the practitioners do, and partly what I do also, is they just say, oh, there's this cute tool, this NTK, there's a hammer. Let's go and look for nails. I mean, that's how they do it. And the surprising thing is that they get state-of-the-art results with this hammer-nail philosophy without much understanding why it works. Right? So, and I'll give you a few of these examples. So one will be the first one that I probably won't get today, but we'll get to next time, is data distillation. So state-of-the-art of data distillation, data set distillation, I should say, is now done with NTKs. And we know the NTKs don't work for many things, right? But for some reason that I'll try to elucidate, for data distillation, data set distillation, the NTK gives the state-of-the-art. And why? Because it's such a difficult problem that even with its deficiencies, even though it's a hammer and I'm half blind or whatever you want to think about it, I still get the nail best than any other tool. Basically, that's the answer, I think. The other nice thing about NTKs is, so we have all these theories, and I'll give a primer of what we really need. We have in particular closed form expressions, and Yasaman gave the recursions, but you can actually compute these recursions. Or if you can't compute these recursions, you can go on. There's now the neural tangent library, which is a fantastic tool. I mean, it's a Google, I think Google, is it Google? Nikos, Google, right? Let's see where Nikos, this is a Google tool. Beautiful tool where you can just take these kernels and you can take a derivative with whatever you want, respect, and it just works. So that's also one driver of progress. It's not only the theory, but also the programming. So what are some practical questions that neural tangent kernels help us solve? What do neural nets learn first and what do they learn last, for instance? And I think already tomorrow probably I'll give you just the expressions that we get from the neural tangent kernel. And if we do a spectrum decomposition of the NTK matrix, and we look at the data, we can see which pieces of the data are learned first and which ones are learned later. Because the convergence of I'll give you maybe I'll write it today or maybe next time. You can write down how fast does training converge with the NTK. I don't know if Andrea has shown this to you. Has he? No. Yes? So basically, how quickly does the training loss decrease as a function of the neural tangent kernel? Have you seen this? The formula? Yes? No? No? I'll write it down maybe today or later. So you can look at this formula, and then you can take data, and that's that beautiful work in the last 2 years. Look at the data, say sampling from the sphere or something like this, and see how does it project on the gram matrix of the kernel, on the eigenspectrum, and which pieces of the data are learned first. Which ones correspond to the large eigenvalues and which ones correspond to the small. Because the large eigenspace is learned first. And you see, I'll speak a bit more about this when I write the formula, you'll see that the low frequencies correspond to the high eigenvalues, so they're learned first. And you have heard of the spectral bias, I think, which says, we learn the easy features first and the complex features last. But with the NTK, you can actually decompose it and give it some sense. You can actually compute these things, right, on some examples. So what features do they extract? Same story. I know we know there are features they don't extract, but if you think of features as in which eigen part of the eigenspectrum they learn, you can make statements, right? Right. So there's lots of beautiful work, and I think partly I see it in posters here. So probably some of you are authors of this, I presume, of how learning looks like. Is it more linear in the beginning? Is it more chaotic in the beginning, like just neural net learning? How close is it to the NTK? And there's some theoretical work on this that shows, for instance, that in the beginning, learning is more linear, and then it becomes more nonlinear. Or the other way around. It depends on various models. I want to talk about data set distillation. Pruning of networks. So this is something in architecture search, kind of a dual problem. Lots of work, paper after paper, about architecture search. And what people do is they have the craziest architectures, and they just search the architecture space to find the best. Because here we saw a convolutional network work well for the data, but that's kind of we knew. But sometimes the inductive bias is not so visible. Can you speed that up with NTK? Yes, they do it. They just brutally take the NTK of look at the eigenspectrum and say, oh, this is the architectures we choose. I'll give you a little more of an intuition. Nobody knows why it works. It works, but with so many approximations that nobody justifies. Again, something you could look at. Adversarial robustness has already some work, and that's partly what Nikos and I and another student have worked on. What can NTKs tell us about adversarial robustness? And among all these open problems in neural nets, this is one of the biggest ones. Because state-of-the-art in adversarial robustness is abysmal. It's okay, but it's terrible compared to state-of-the-art in standard learning, right? There are some algorithms that are NTK-inspired, poisoning attacks. What is poisoning attack? Is how do I change my data, the training data, a little bit so that I fool the neural net to learn something else? Okay, poisoning attacks, NTK-based. Catastrophic forgetting, I think I might not get to it, but Chaim alluded to it. So he had a bit of a, where's this? There was one student who was an expert on this. I forgot who. Maybe he's not here. Sebastian. Maybe he's not here. But anyway, so Chaim alluded to it, and he looked through kernels at catastrophic forgetting, how much is retained. So again, what can kernels tell us about this? There have been recently, in the last, again, year or two, papers that used NTK to do problems like matrix completion. Generally, NTKs seem to be good for small data tasks, which might explain why dataset distillation works. Very recent paper, recommendation networks with the NTK, understanding ensembling, all that are open questions that I might or might not get to with the NTK. So, yes?
When you say NTK, is it all the same to you? Would you say kernel method, or does it actually matter that
this is an excellent question. Yes, so you would wonder why not a Gaussian kernel, and again, there's only empirical answers here. So the NTK just works, and the Gaussian kernel doesn't. Why? Presumably because it does describe some limit, right? It does describe the infinitely wide limit because you can into the NTK put some architecture. There's a convolutional one. There's a fully connected one. There's even one for physics-inspired neural nets. You can build the NTK. So presumably you can endow it with the architecture.
For the convolutional, I would kind of understand if there is some locality in the task, like the example CK. But are there cases where actually the fully connected NTK is actually better than some of these like standard?
The answer is more pragmatic than that. It is easier to compute the fully connected kernel for large. As you know, kernel methods have one big disadvantage. They scale badly with the size of the data, as we all know. I mean, you know, it's like the matrix is n by n. N by n in this case, right? So it's, if you have to invert the thing, it's it's more than quadratic, right? So it's easier to invert a fully connected kernel corresponding to a fully connected one than to a convolutional one, which is why sometimes the convolutional works, the fully connected works better because we just can't do a convolutional of that size. So it's more a pragmatic. I presume the convolutional would always work better for practical problems, but sometimes we can't compute it as an answer. All right. I think, so why do we like NTKs? First of all, kernel-rich regression is simple. People understand it. There's a closed form, and we can take derivative with respect to the data of the kernel, which is very hard to do for a neural net when you have to, go through all the gradients. And so to Lenka's questions, yes, they seem to describe something. And there are, in fact, when you look at the results that, the convergence result that Yasaman alluded to when you let all the widths go to infinity, the question is at what rate, right? I mean, how does the distance to the NTK from the normal, so let me write this down perhaps, because this is important. So Yasaman hasn't, I don't know Yasaman if you will, but you haven't spoken about learning yet. But one of these nice things of the NTK is that it describes how neural nets learn also. You have just described the process so far. But when we look at these bounds that have been shown by all kinds of groups, including the Google group, then they all, let me just try to write down the bounds. They all have this kind of form. Let's see. So I guess I don't need to tell you what the NTK is, right? But let me just write down in my notation what I mean. So generally, as an NTK, we think of it as the entries of the NTK as these feature vectors here, right? So my weights are now parameterized by theta, right? On x, sorry. This is the function of the neural net. These are the initial weights. This is the data. And the NTK is formed by these gradient vectors, right? X prime. Right? So we have all seen this formulation of the NTK. Okay? And normally the flavor of the results is that let's assume we have layers width D1, DL. These are the width of our various layers. And let's assume they all have width M. And then we let M go to infinity. So Yasaman spoke about, there's a series of papers, I think from the Google group, that basically shows sequential going to infinity. So first the first layer, then the second, not the first is the data layer, but the second layer, the third layer, and so on, they go to infinity one by one, and you get this approximation, okay? But then there are also results that basically let all these layers go to infinity at the same time, with like M, okay? And then they prove bounds as a function of M, right? Bounds on the kernel. And these bounds basically, in particular, show. So this is the neural tangent kernel at initialization. And you could look, in principle, for a neural net, this thing is changing in time, right? So as the weights change, the kernel will change, okay? But we know that for very wide neural nets, the kernel, even when the weights in time, doesn't change much. And in fact becomes constant in the infinite width limit. And then the question is how fast, right? And so the kernel at initialization, so this is the kernel at initialization, and you can generally have a kernel when you don't have this, but just have this as a function of time instead, then it's the kernel at time t, right, when you do learning, okay? And so the flavor of the result is usually that people bound this type of thing, right? And so these bounds say we want to make this smaller than epsilon, right? Very small. And then the question is, how does epsilon scale with this width, right? This is kind of the trade-off that people are trying to prove, okay? And when they do this, in particular, there's one type of results where in order for this to be very small here, for some very small epsilon, m needs to scale polynomially with the number of data points and the smallest eigenvector of the kernel matrix. For instance, this is one. Have you seen these type of results? Has Andrea shown any of this? I'm sorry. I'm sorry I missed this. But did Andrea show something like this? No. Okay. But will you show this? Yasaman? Okay. So, but will you? Okay. So you will see it. But the point is, of course, for the practitioner. Okay. So they look at this, and then they use these results in order to basically argue about the data, argue about the smallest relevant eigenvector, and then say, for instance, if this eigenvalue is pretty large, I mean, relatively speaking, then, sorry, should it be 1 over lambda? It might be over 1. It depends on how, I mean, the point here is the larger this thing is, the less m you need. So I should maybe write, what should I write? The larger, so maybe we will write it as 1 over lambda. So the spirit here is, let me write it. The spirit is, if this is relatively large, right, relatively, then m can be relatively small, right? So these type of results, basically for the practitioner, they then look at the kernel matrices, they look at the relevant eigenvectors, because sometimes not all eigenvectors matter, depending on the data, right? You look which ones, where the data projects, right? And then they say, oh, we only need, even for narrower networks, we still get good results, right? So this is one type of argument. And this is also something, for instance, in this work that I mentioned about the spectral bias, these Fourier components. What they find is that if the Fourier components, if there is a low frequency, then the data projects on the high eigenvalues of the kernel. We can forget the low ones, so effectively this thing becomes larger, and so narrower networks are good at picking up these frequencies. You with me? And you need wider networks to pick up the high frequency part. Yes, sorry.
I'd like to make a comment and a question related to that. Infinite width limit is not synonymous with NTK, right? You can take infinite width limit and still have the future loop. Now, here, this result is in fact a condition under which the feature don't move.
Yes.
But, I mean, okay, so that's a bit like, inward looking, which is to say that's to remain in the NTK. But why do we care? Like, the fact that the kernel doesn't move doesn't give you guarantee that you will learn better this way than if the feature.
I agree. I agree with you. I agree. Here it's more, again, these results are still on an intuitive level, but they want to explain why is a narrower neural net good at picking up low frequencies, and when you need wider ones for high frequencies, and then you go to the NTK regime and say, okay, for low frequencies, you are already in the NTK regime. There we can decompose, and hence we see it. I agree that this is a bit of an argument like this, but it still gives an intuition of why this is true. I agree. Right, and so, in fact, several algorithms look at the smallest relevant eigenvector of some NTK matrix. They don't even go to the NTK regime. They just empirically compute this type of feature vectors, look at the empirical NTK, so to speak, look at the eigenvalue decomposition, and make conclusions about how well the thing trains, what it learns, and so on and so forth. So all I'm saying is all that theory actually can give intuitions on all these practical questions about spectral bias, what widths one needs, and so on and so forth. Okay, so this is one type of result that is important. And let's see what else I wanted from my... how many minutes, Lenka? Should I stop early or shall I... Okay, so let me just one more. What do I have here? Right. So just this is in the spirit of what I said. So what the practitioners do is the common approach is, let's start with some problem for a neural net. We can't answer it. Let's look at the NTK. Either go to infinite width or just compute the thing empirically by computing this thing. Solve it, and miracle, it works. So there are lots of these. And why does it work? That's for you to answer. So there was one more thing that probably many of you have seen, and I know there's a whole crowd here that is thinking about random labels. So this was a nice result. This is Aurora et al. 3 years ago, where they basically, who has seen this? I'm just wondering. Oh, okay, some people, but not everybody. So it's in the spirit of what I said. Let me just write down one formula so that that it's a little bit easier. So in particular, convergence during training. During training, okay, at training. So what you can show, basically, is that the L2 distance, right, so the loss between what your neural net has learned in the NTK regime, say, minus the actual labels. Okay, so you want to converge to your labels, and that loss is basically, roughly, the sum of the spectrum e to the minus the eigenvalues of the NTK, and then the eigenspectrum of the NTK projected on the labels of the data. Okay, so what have I written here? When we think of the NTK as k, then we can write it as an eigendecomposition as lambda I to m, n in this case, v I transpose, right? So this is the eigendecomposition of the Gram matrix of the NTK, right? And what you can show when you view it as a flow with learning, I guess there's a learning rate here. Maybe think of a constant here. It doesn't matter. But the point is, learning happens in the various if you look at it in the eigenspace of the NTK, then we learn for the large eigenvalues, we converge first. And for the small eigenvalues, we converge last. So in particular, what they have done is they have just taken MNIST, 2-class MNIST, whatever, 2, I don't know which numbers they have taken, 0, 1 or something, and they have projected it onto the NTK spectrum of some neural net. I think it's like a 2-layer net or something, right? And they have seen that if you have normal MNIST, it's very tightly concentrated on the top eigenvectors of the NTK. Of that neural net. And if you do the random label business, let me just finish my sentence, then you are totally spread out. Okay? And that explains, at least then you can see why it takes so much longer to train with random labels than it does to train with MNIST labels. Yes?
Is this from all different weights? And is this
this is in the NTK regime, yes. Yes. Like 1 over whatever it needs to be, yes.
Is this a linear or non-linear?
I think this was a nonlinear, but I'll go back, I'll answer this question offline. But yes, I think it's like a real neural net. This is just okay. I mean, there's not much theory here because all they do is they observe how do we see convergence at training. Okay, we can look in the eigenspectrum of the NTK, and lo and behold, MNIST data has this weird kind of shape. Nice. But then also, and when you do random labels, it's all over the place, and hence it takes much longer. Okay, I mean it's not very scientific, but it gives you a different lens on this problem. And they do it for CFAR, and there it's already less clear. They still have a large concentration on the large eigenspectrum of the NTK, but then it's more spread out. But of course, with random labels, it's just a mess again, and it takes forever. So that's just one of the things that the NTK allows us to look at differently. Questions? If not, I think I'll stop here and then. Oh yeah, so last thing is you have seen this I didn't know, yeah, someone would give you all the gory stuff. But one nice thing is you can actually compute all these things. And you can actually, once you write down a nonlinearity something, you can actually get really nice expressions. I mean, these don't look so nice, but they have been done also for the convnets. And you just write them down and you have some iterative expression and you can just take a derivative with respect to x, for instance, not you, but the library. So this is useful for us, for people who want to compute things. Just saying. So I think that was all I had to say, and then I'll go back to this and start here next time, tomorrow.